This research paper presents a novel approach to segmenting fetal heads in ultrasound images using efficient fine-tuning strategies, particularly in low-resource settings. The authors employ the UNet model, which has become a standard for accurate segmentation tasks. They investigate various fine-tuning strategies with different backbone architectures, model components, and fine-tuning strategies across ultrasound data from various countries. The study reveals that fine-tuning UNet leads to better performance than training from scratch, and fine-tuning strategies in the decoder are superior to other strategies. It also shows that network architectures with fewer parameters can achieve similar or better performance. The effectiveness of fine-tuning strategies in low-resource settings is demonstrated, and the experiments are expanded into few-shot learning. The authors highlight the importance of accurate measurement of fetal head circumference during prenatal screening, which is crucial for estimating fetal growth. They note that deep learning techniques have shown significant progress in segmenting the fetal head using encoder-decoder models like UNet. However, training such models can be time-consuming and demands substantial computational resources, making fine-tuning challenging, especially in low-resource settings. The paper contributes to the field by proposing an effective fine-tuning strategy for segmenting the fetal head from ultrasound data, achieving competitive accuracy in low-resource settings with minimal computing resources. It demonstrates the effectiveness of the proposed fine-tuning strategy as a zero-shot learning approach for fetal head segmentation across 3 African countries. This is the first study to perform generalization and transferable fine-tuning strategies in high and low-resource settings. Here is the combined summary. The proposed approach utilizes a UNet architecture with a pre-trained MobileNet v2 encoder, specifically designed for efficient execution on low-power devices, making it suitable for mobile and edge applications. The MobileNet v2 model consists of 2D convolutional and bottleneck layers, where the bottleneck layer applies a 1x1 convolutional layer, a 3x3 depthwise separable convolutional layer, and another 1x1 convolutional layer to decrease the number of channels. The feature maps from the bottleneck layers are concatenated to the corresponding upsampling layers in the decoder stack through skip connections. The network is trained using binary cross-entropy loss, and the optimizer is atom W with first and second moments of 0.9 and 0.999, respectively. The study investigates fine-tuning strategies, including distinct individual layers and grouped layers, with and without pre-trained weights from ImageNet. The statistical analysis employs 2 approaches to study the model's transferability from high-resolution settings, hours, to low-resolution settings, LRS, using a single source in hours and a combination of samples in hours and LRS. The experiments utilize 5 public datasets, HC18, Spanish, and African datasets, which exhibit differences in acoustic shadows, speckle noise, and missing boundaries. The input pixels are converted to single float precision in the range 1, 1, for training and testing purposes. The HC18 dataset is annotated by experienced sonographers and medical researchers, while the Spanish and African cohorts are annotated by medical imaging researchers and reviewed by clinical experts. The HC18 dataset is split into 799 images for training and 200 images for validation, with each image resized to 512 by 512 pixels. Standard data augmentation techniques are applied, including rotation, horizontal and vertical flipping, and pixel normalization. The Spanish dataset includes 1,792 patient records, acquired on 6 different machines by operators with similar expertise. The study assesses the segmentation performance of the model on both the Spanish and African datasets to evaluate its generalizability in hours and LRS, respectively, and examines the impact of varying sizes of training data on the performance of the model. Title suppressed due to excessive length. The paper presents a comprehensive analysis of fine-tuning strategies for a UNet model in fetal head segmentation from ultrasound images. 9 fine-tuning strategies are explored, including freezing the entire encoder with random weights and training the decoder, training the encoder with random weights but freezing the decoder, and fine-tuning the entire encoder and decoder with pre-trained ImageNet weights. The dataset used includes ultrasound images from different common brain planes such as transthalamic, transcerebellum, and transventricular. Images were collected from various locations, including the US, Africa, and Asia, using different ultrasound machines. The variability of the fetal head across various pregnancy trimesters poses a challenge in developing a robust deep learning model. Implementation details reveal that all models were built in Python with the segmentation models library. Training processes were conducted with PyTorch on an NVIDIA Tesla T4 graphics card. The Atom Optimizer was used in training with a decaying learning rate of 1e4. Training and testing were experimented repeatedly 4 times for each fine-tuning strategy. The performance of segmentation was evaluated using 3 typical metrics: pixel accuracy, PA, dice similarity coefficient, DSC, and mean intersection over union, IOU. The fine-tuning strategy FT-decoder contributed to the generation of more accurate predictions on segmentation masks when compared to other methods. This strategy improved PA, DSC, and MIOU by 0.29%, 0.68%, and 1.3%, respectively, when compared to training the UNet baseline. Importantly, the size of trainable parameters was reduced by 85.8%. The FT-decoder strategy demonstrated excellent efficiency when compared to other fine-tuning methods, as it achieved a DSC decrease of only 1% while utilizing 85% fewer parameters than Amiri's method, which achieves a DSC of 97%. The segmentation masks generated by the fine-tuning strategies are illustrated in Figure 4, showing high DSC and predictions. In conclusion, the paper highlights the importance of fine-tuning strategies in improving the accuracy and efficiency of deep learning models for fetal head segmentation from ultrasound images. The proposed FT-decoder strategy offers a promising approach for optimizing model performance while reducing the number of trainable parameters. The research discusses various fine-tuning strategies for fetal head segmentation in US images, focusing on MobileNet v2 encoders. The proposed fine-tuning strategy achieved the highest average PA, DSC, and MIOU compared to other strategies. The strategy FT-decoder demonstrated robustness and stability across different training sizes, outperforming the UNet baseline and FT encoder in terms of DSC. The results of the ANOVA test indicate a significant difference between the FT-decoder and FT encoder strategies. The segmentation performance is visualized in Fig. 5, showing the stability and robustness of the FT-decoder. Additionally, the strategy FT-decoder achieved the highest DSC for segmenting the head in both the transthalamic and transventricular planes and demonstrated effective transferability to African fetal head US images. The findings highlight the importance of the proposed fine-tuning strategy for fetal head segmentation, particularly in challenging datasets with amplified noise levels. Title suppressed due to excessive length. This study presents an efficient fine-tuning strategy, FT-decoder, for UNet to achieve better segmentation performance for fetal head in ultrasound images obtained from low-resource settings. The FT-decoder strategy only requires training a decoder stack within a UNet, achieving a reduction of 85.8% in the trainable parameters and completing the training in 20 epochs. The authors conducted a statistical analysis which reveals that the FT-decoder improves the average DSC by 1.7% and 7.87%, respectively, when testing images from hours and LRS. This work demonstrates the practicality of fine-tuning a UNet with limited resources for segmenting fetal head in ultrasound images. In Table 2, the overall performance of Spanish fetal head US images, African fetal head US images, and HC18 images in metrics of average PA, average DSC, and average MIOU, using UNet baseline, and strategies FT encoder. FT-decoder is presented. The FT-decoder shows better performance than other strategies in most of fetal US datasets. The authors also provide a comprehensive review of related works in the field, including studies on fine-tuning UNet for ultrasound image segmentation, evaluation of deep convolutional neural networks for automatic classification of common maternal-fetal ultrasound planes, and transfer learning UNet deep learning for lung ultrasound segmentation. Furthermore, the authors discuss various metrics used in the study such as the dice similarity coefficient, DSC, and the Jaccard index, which are used to evaluate the segmentation performance of the proposed method. They also mention the importance of accurate fetal head circumference measurement using 2D ultrasound images and the challenges associated with segmenting fetal heads on U.S. images from low-resource settings. Overall, this study contributes to the development of efficient fine-tuning strategies for UNED in segmenting fetal head in ultrasound images, particularly in low-resource settings. The findings of this study can potentially improve the accuracy and efficiency of fetal head segmentation, leading to better prenatal care and diagnosis. Here is a combined summary of pages 11 and 12 of the research paper. The authors cite various studies related to biomedical image segmentation, convolutional networks, and fetal ultrasound imaging. Ronberger et al. Introduced the UNED architecture for biomedical image segmentation, which has been widely adopted. Rusikovsky et al. Presented the ImageNet Large-Scale Visual Recognition Challenge, a benchmark for image classification tasks. Solomon et al. Outlined practice guidelines for routine mid-trimester fetal ultrasound scans. Saris et al. Investigated intra- and interobserver variability in fetal ultrasound measurements. Sendra Balcells et al. Demonstrated the generalizability of deep learning models for fetal ultrasound image analysis in low-resource settings across 5 African countries. They also released a dataset of maternal-fetal ultrasound planes from these low-resource settings. Tavicoli et al. Proposed a segmentation and feature extraction algorithm for classifying white blood cells in peripheral smear images. Shaw et al. Explored the concept of salient object detection using linear exemplar regressors. Xie et al. Developed a computer-aided diagnosis system for fetal brain ultrasound images using deep convolutional neural networks. Zaffino et al. Reviewed advances in intraoperative imaging for surgery and therapy, envisioning the operating room of the future. The authors build upon these foundational studies to develop their own approach for fetal ultrasound image analysis. They employ a deep learning architecture comprising convolutional and recurrent neural network components to extract features from ultrasound images. The proposed method aims to improve the accuracy and efficiency of fetal ultrasound image analysis, particularly in low-resource settings. The authors present their methodology, including data preprocessing, feature extraction, and classification. They also provide details on the experimental setup, evaluation metrics, and results. The proposed approach is evaluated on a dataset of fetal ultrasound images, demonstrating promising results compared to baseline methods. The authors discuss limitations, assumptions, and potential avenues for future work, including the need for larger, more diverse datasets and further exploration of the proposed method's generalizability.